Welcome to this webinar about new motors specifically for format change and setup access. So I'll be your host. I'm Kenneth Hayden, Area Sales Manager, and I have a co-host, Palle who will help me. And we're going to start out with looking at just a short who is JVL, and we're going to look at the background for the ServoStep motor, and then we're going to jump into this new version specifically for format change. So let me introduce Palle Sorensen first, who is going to introduce you to the ServoStep motor and a little bit about JVL. Over to you, Palle.
Yeah, hi. First, very shortly about JVL. We are Danish independent designer and manufacturer of integrated servo motors, stepper motors, and motion control products. The company was founded in 1985, and it is still owned by the two original founders. We have high quality in production and development. We are ISO 9001 approved, and we have a close cooperation with our distributors, OEMs, and other partners. JVL is actually the inventor of the first integrated servo motor, and we have strong R&D and technical support. And perhaps we can get this slide on here. One moment. Yeah, this is your host today, Kenneth Pilheden, and myself, and Kimi Lauritsen, who is our producer today, I should say. Okay, so let's see if I can shift to the next slide here. I have a little technical problem here. Let's see. Yeah, so just to show you our portfolio, as mentioned, we have integrated stepper and servos on our program, and this is our range for DC supply or battery supply. So that's small servo motors, integrated servo motors up to 400 watt, and our whole range of ServoSteps, as we call them, integrated stepper motors up to 25 Newton meter. And then we have our AC supplied portfolio, and that's integrated servos up to 4,500 watt. And so, of course, you want to know what is an integrated motor actually. It's a servo or stepper motor where everything is built into one compact unit. So you have the motor, either servo or stepper. You have hall sensors. You have an encoder. So that's the feedback. The encoder is mounted on the motor shaft, and that means you always have feedback of where are the shaft right now. So you never lose position information. And it can be incremental, meaning that it just gives you pulses when it moves, or it can be absolute multi-turn, meaning that even though you switch on and off power many times, you still have the correct position in your system. And this is actually, of course, very important for format change. And it also includes power electronics, an advanced controller with a fast CPU, and as option, an Ethernet board option with an embedded Ethernet switch. And in the servos, as mentioned on the previous slide, then you also have built-in power supply. So you can directly attach 230 volt AC supply, one phase, or three phase 400 volt AC supply. And we call our integrated stepper motors ServoStep. And here's a very short comparison to a standard stepper. As you will notice, you normally need a very high safety margin compared. I mean, you have your motor torque, and then you need a safety margin down to the available torque, because if you don't operate with a safety margin, the stepper motor can stall. But that never happens with our ServoStep system. So that means you can almost utilize 100% of the motor torque with a ServoStep. This is a slide I've included from the previous video. You can click below for a link to the previous webinar video. So you have completely stall-free operation. You have the best efficiency. We had a use case where we had a battery supply, and we had up to 93% better efficiency when we ran with closed loop than with open loop. And open loop is the same as a traditional stepper motor. We have no resonances, so the start velocity that you normally would use for a stepper motor is not needed. You can run with a higher acceleration and speed, and you have easy positioning, also if the motor is overloaded. And again, you can utilize your motor almost 100%. And I think that's basically it. So I think we go back to my colleague, Kenneth.
Yeah. Okay. So thank you, Palle. So what we've done to increase the usability of the ServoStep motor is we've changed the front, the shaft, and I'll just show you an animation here of what we've done. So we've taken the normal small shaft and put a 14mm shaft. We've completely changed the front and added a huge double bearing, so you can attach timing belt wheels directly to the shaft. And then we've also done a hollow shaft. So by replacing the standard shaft with a hollow one, we have enabled the possibility to mount the motor directly on a spindle. And we've done this in two different versions, one with a clamp, and then one, as we see here, with a smaller, more compact version where we put a pin through the spindle. A big difference in terms of doing this is the mounting. So instead of mounting it on the 4 holes in the flange, we're mounting it directly on the spindle, having the motor actually float. But to do that, we're going to need an anti-rotation device, so it doesn't turn with the spindle. And here's an example where we're using a bracket and an anti-rotation pin. So the final solution is really a super compact spindle drive. So let's go into detail about this and why this might be a really good idea for you.
Yeah, I think it's a little slow changing to your presentation.
I think it is, but we will get there.
Eventually.
Eventually we will.
Yeah.
We cannot see it.
Okay, I think we should be.
Yeah, now I think it's there. We have the background photo.
Okay. So these are the motors that we just saw in the animation. So we have the large front shaft, we have the clamp, and then the mini clamp, or with the pin through. And the kind of application that we've designed this for is replacing hand wheels. And here's a good example from a packaging machine. And the disadvantages of doing it with all of these adjustment wheels is that it's really slow. It's going to be a long downtime. If you're only doing this once a month, it really doesn't matter. But if today, when you're doing a smaller and smaller series, this could be a big thing. And the error chance is really high because since it's done manually, you're going to have an operator in the production adjusting every wheel, and it is a possibility that he could forget one. Repeatability is also low because of the manual adjustment every time. So you really, to use hand wheels, it's going to require high volume. But on the good thing, the initial investment is low. So why would we want to use a ServoStep for this? Well, first of all, I think it's for reducing the error risk. The operator error can be, really a big thing. You could lose a whole production. And then the minimum downtime, because part of reducing your cost if you're doing a smaller series is the time it takes to set up between different package sizes or product sizes. Benefit one. So compared to all other solutions, here you can jog from your laptop. So you can either type in a position, or you can just slowly move it and hit up against a mechanical stop, or you could reach a sensor. And then that could be your new 0 point, or it could be a new position. And benefit two is you can see your feedback. So you can see your position, again, from your laptop, and you would also be able to get a confirmation that all of the different axes have reached their destination, so you're now ready to change over and produce this new box size. You also have embedded diagnostics, so if something goes wrong, you can react to it. And that could be anything from the motor not reaching its destination, something could be stuck, maybe a box from the former production, or it could be an error on the motor. It could be overheating because it's working, or whatever it could be. Benefit three is the motor has a really high torque. This comes from the step motor technology together with the ServoStep, and you're able to utilize. So it's compared to the size, it's 10 times stronger than a servo motor. And this will enable you to mount it directly on the spindle without any gear. First of all, saving the cost of the gear, but also reducing your mechanical tolerances since you're directly on just that one mechanical part. So you'll just have the nut on the spindle giving you your tolerances. You also have fairly high speed. And since this isn't the first time a product for this kind of application is made, speed is a really good thing here, because some of these other solutions have several different gears, making it run anywhere from 5 RPM, 10 RPM. And here you could actually run up to 3,000 RPM. So if this is really something that's necessary on your machine, you could do really fast changeovers, or it could be part of your production. Benefit four, it's compact. It's about the same size as a hand wheel and a manual digital showing, and the little digital display that you have on that. But most importantly is you don't need any space in your cabinet. So you could have 25 motors, you could have 30 motors on one machine, and you wouldn't have to invest in a new cabinet because everything is inside the motor. Benefit five, no dip switches. Now, this is again compared to a competitor solutions where you would have to change something. You'd have to open a little lid and change something manually in the motor. That means you would have to get up from your laptop and go into the production and change something. So everything here is software, and especially the reset of the position as well. And because some of these solutions actually require that you manually remove the motor, change the position, then put it back. So this isn't an issue here. Everything software directly from your laptop. It's fast. You could be up and running with our MacTalk software in a few minutes. You could start doing your first moves, or you could use the embedded PLC and do a quick program. And you also have support for all major Ethernet protocols. And specifically for Siemens, there are function blocks. And for an Allen Bradley or Rockwell automation system, there's an add-on instruction specifically made for format change applications. So if we could look at the details more mechanically, so it's a NEMA 23 motor. This means that it's a 57 times 57 millimeter flange. as we saw in the animation and the mounting example, we really don't need the flange, but it gives a good idea of the size of the motor. I could help with that. Here you have exactly the motor we're talking about. So you have the hollow shaft with the clamp or the pin, and you have the shaft specifically for a timing belt. And just to mention on the timing belt, if you were to add a timing belt directly on a normal motor with a small shaft, that bearing wouldn't be able to hold that force that you're putting on there with timing belt. So this is really necessary if you want to mount a timing belt wheel.
Yeah, and I would add that as well, that the small shaft, 6 point something millimeters, it could easily break.
Yeah, it's just too small for that. You would need an intermediate bearing housing and an external shaft.
Yeah.
So, and this is a huge double roller bearing that we put in there with a 7,100 Newton meter force capability. And it just really makes a big difference so that you can just use the motor directly for a lot of applications. We also have standard spindles available. So to get you started, you could get a spindle directly from our stock, but we also provide a drawing of the spindle and the mounting part for that spindle, so you could source this yourself or make it in your own workshop. The motors have a 2-port Ethernet switch, and this enables that if we do the example again with 25 motors, then you can daisy chain with one Ethernet line between all the motors in your factory, making it, again, really fast setup. So there's also a smaller version, a NEMA 17, to give you kind of an idea about that. It's a little bit smaller, and this is also available with the same kind of hollow shaft, but with a pin. And if you need the clamp, we provide a gear giving a higher torque and just a slightly larger package. So there's also standard spindles available for this, or we provide, again, the drawings if you want to source them yourselves or make them in your own shop. And using the gear, you can get a very high torque. And the NEMA 17 motor is also very fast, so you can get a very, very small format change motor by combining these two. Safety. This is always a big issue, so I am happy to tell you that all of the motors here have a possibility of choosing an STO, a safe torque off, which is an extra M8 connector, and this is approved and certified for SIL 3. And let's go into detail of the different variations. So if you know JBL products, you'll know that you can customize and choose a whole bunch of different options, and it can be a little bit tricky to kind of figure out what we're looking for, and especially now if you find this interesting and that you would want to request a quote afterwards. So first thing is the encoder. So you have the standard semi-absolute encoder, which is the H2, or you have an absolute multi-turn encoder with this is an H4. And make a note that the H2 is semi-absolute, which means that it will notice where it is within 1 revolution, even if it's off. So if you have a machine like the packaging machine we saw before that's completely covered, and you know if somebody was in there, you could use that and save a little bit of cost. But you would need to have some sensors to make sure that nobody has touched anything. Connector orientations. So you'll find an S or a Q in the product code. I'll give you an example on the next slide. But the S is that you have your connectors to the top or to the side, whatever you want to call it. Or Q, you have all your connectors to your rear. And then you have an availability to also choose between a standard IP42 or go with an IP65 version. And take note that these motors do not support an IP65 front, but you have a possibility of having the back of the motor coded, and the connectors are always IP67. So the actual product codes, so if, let's say if we look at the clamp version, here's what you want to make a note of, is that you want an S67 version. So you have the original ServoStep motor, the MIS232, S67. This will give you the front clamp. And then the rest is where you choose what kind of connectors you want, and which Ethernet protocol that you want it to support. And if you like a little bit smaller one with the pin, then you want the 66 version, S for the connectors on the side and the Q for the connectors on the rear. And if you want the timing belt with the larger shaft, it's the 49 version. Again, S for the connectors on the side, Q on the rear. And then you have these ultra high torque versions, which have a different code. So it's a T for the connectors on the top and an R. And these are about the same size as a 232, if you know these motors, but with a 2.53 Newton meter, which is really extreme for this kind of sized motor.
But can I just add that in between those two, you actually have a MIS 232 in S and Q version as well. So we have the whole range from almost 1 Newton meter up to 2.5 Newton meter.
That is correct. And if you want to look at the NEMA 17, so here's the gear, and this is where it's an HS HG, but with a 39 in the end. And I'll go back and show you on the website afterwards where we can find these. So that's it for the slide. I'm going to switch over to the website. Okay, so the motors are found under integrated stepper motors. And if you're looking for these, you want to go for the MIS 232 series and look for an option. So first we have the standard option, and if we scroll a little bit down, you have these special options right here. So let's look at the clamp one. And here you basically get all the information, get a detailed sketch of how we built it. And we also provide, of course, the drawing and also the spindles that match are right below here. So here you could either have the product code for a stock spindle or the drawing if you want to source your own spindle or even make it yourself. Now, if you're looking for the 17 version, you'll want to go through products and look for gears, planetary, robot, and worm gears, and the NEMA 17 gear version. And here you see a few of them, and then you have the direct product codes right here. So these are the same product codes that I referenced, and with details and the drawings. Okay, so that was basically the new product launch of these new motors. So it's an MIS 232 with a lot of options, and let's hear some feedback. And let's have some questions. Or Palle, do you have anything else that we want to add today?
No, I think you covered pretty much what's needed for this product series.
Okay.
So perhaps we have some questions already, or let's hear Kimi.
No questions yet.
Okay.
But they are 30 seconds lagging in time. So let's wait a second.
No problem. So in between, I'm just going to go back and show you something here on the, so we get some of the details here in place. So this is just a detailed drawing of the internal of the pin version. So you have a threaded part in the bottom to pull the shaft in there, and then just show you a drawing of the spindle as well. And here's an example of a spindle that fits into the pin version. So a lot of these is fairly is easier. It's more locked into specific part numbers than we're used to. You can configure all different variations, but please ask us in terms of what we carry in stock to avoid a longer delivery time.
Good. We have a question, Kenneth.
Yeah, sure.
What are the typical application for these new motor types?
That's a good question. So format change is really broad, and the example I gave, that machine was a packaging machine, and so actually any kind of machine where you do have a hand, where you traditionally would have done these changeovers with a hand wheel, that's where you'd want to add this. So if you're building let's say a brand new machine, you could consider an electric actuator for some of these movements. But if you have let's say a historic machine which you want to upgrade, this could also be as an end user that you want to upgrade this. This is where you really want to use this kind of motor. Or if you just want to reduce the size. If you were to compare let's say a standard solution where you have a spindle, a bearing housing, a coupling, maybe another bearing housing, and then the motor, you'd probably have maybe a 50% shorter solution. And using less parts, and that will also save you cost. So I can't tell you exactly where, but I typically would see this in a packaging, anywhere where you have, the boxes change sizes in your production. Any other questions, Kimmy?
There is one. Are the pin and hollow shaft motors longer than the normal? Peter has answered, but I think it is a good one for everybody.
Yes. So the motor is a little bit longer because of the larger bearing. And specifically, you would have to compare, but it is longer. So if you take a 231 and compare with a 231 with its larger bearing, it's about 20 millimeters longer. But then plus the clamp, or plus the if you're looking at the pin version, the part that sticks out. But the overall length, if you were going to use a standard one with a coupling, would still be much shorter.
And then we have one. Where do I find the RA add-on instruction?
Sorry, please repeat.
Yeah, that must be the Rockwell automation add-on instructions.
Yeah, that's a good question. So I'll just show you that here. So you just want to go up on downloads, software, and there's a directly for Ethernet Ethernet configuration files. Ethernet IP add-on instructions. It has its own page. And here you have the add-on instructions for the ServoStep motor and the add-on instruction for the servo motors. And
I think you should mention here also, since the question was about add-on instructions, that JVL is a Rockwell partner.
Yeah, of course. Yeah, so we're a technology partner with Rockwell. So Rockwell has been involved in developing these add-on instructions to really make it seamless. So anyone using Rockwell will feel right at home. We've used the same terminology. Everything is named the same way, so it should be really straightforward to implement. Any other questions, Kimmy?
how much is the spindle structure reduced, the efficiency comparing to a normal motor with a rotating lobe?
How much the efficiency?
Yes.
I don't think we have anything that any comparison. I'm not sure.
I also want to know, is the question if we compare a traditional solution with a spindle compared to our integrated solution? I would say that on the mechanical side, I don't think there's any real difference. The big difference is in the drive itself, the ServoStep drive.
He rephrased the question. In other words, how much is the efficiency of rotating to linear mechanical structure?
No, I don't think I'd be able to. I'd have to see. Yeah, if you have a very specific question, I would send that to support, and then we'll look at it specifically for that application. I can't see specifically in what. I can't see the connection to the efficiency of the mechanics.
Yeah, or if the question could be perhaps rephrased, or I don't know, perhaps we can try to answer now. But
yeah, well, I can comment though on the motor in general, because the motor has the ServoStep technology. It also has a current control, and if you were to add a standard step motor for this kind of application, you would have them powered up. And if you were adding 25, you would be using a considerable amount of power. So if you compare to a standard step motor, it would be a huge reduction in power. Because current control would reduce the power to a minimum to keep all these axes in place. So they would basically only use power when you're commanding them to move.
Yeah, a traditional stepper motor you run with the. I mean, in traditional stepper motor, the current that you send into the motor is equal to the torque you can get from the motor. So in general, you would say if you want to utilize all the motor torque, you would send in the maximum amount of amps into the motor. And then there are two things that heat up a stepper motor a lot, and that's the current that you send in, and it's the speed that the motor runs with. And this is let's say basic physical stuff. It doesn't matter which brand of stepper motor you use. And as Kenneth says, if you use one of our ServoSteps with closed loop control, then automatically the controller will reduce the amount of current pumped into the motor windings, and this will give better efficiency, and it will heat up the motor much less than a traditional stepper motor. Yeah.
We have one more question.
Yes.
You mentioned that the spindle motor are not IP65, 56, 65 on the face of the motor, but they are on the back. Is it true of the standard MIS integrated motor as well, that aren't spindle motor version?
No, so there's a big difference. So if you go with a standard MIS motor with, for example, a 6.35 millimeter shaft, you can have a shaft seal for that. So it will be IP65 as a minimum. So for that motor, we do have a solution. So you can't have it on these because of the new design of the bearing. So there's no possibility to seal the shaft on that. So yeah, if you want to go for a higher IP class, you're going to need to look at the standard series.
And any more questions?
No, not at the moment.
Okay. Okay, well, as always, if you have a specific technical question, send it to support@jvl.dk. And if you found one of these products interesting, send your inquiry to sales@jvl.dk. So thank you for watching this webinar. See you on the next one.
Yeah, thank you. Bye.
Bye-bye.